Good morning. In the first two lectures, we had the introduction to the design, how the design process is, what exactly is a process and such details. And at the end of the second lecture, we had come to a point where we were talking about optimal design. And there we had one specific statement which is rather strong, that whenever we are going to design a large system which has got several subcomponents, it is not essential that we would like to perform maximization of each of these units individually. This we had shown on the slide which we had in the last class. Today what I intend to do is basically start from that particular point, and I had committed earlier that we will start with an example of a reactor with a separation system. In most reactor systems, you have a separation section which follows it. It separates the products, makes it recoverable, and then stores it. A typical example that I am going to draw here is that of a case in which there is a reaction A going to B. And I have a CSTR here, I have a feed rate of F, I have the CSTR starting here, and it goes to a column, possibly a distillation column. It could be other type of separation arrangement also, and it produces a product of B. Basically, it is rich in B, which is the desired product, and a waste stream. What I wanted to say is, say X% is the conversion, and here Y% is the percentage recovery of B from the column feed. Now, if you look at these two individual processes, if we want to see the cost parameter which is based on the X and the Y values, we can put it like this: with the conversion increasing, the rupees per metric ton of B will keep on reducing. That means, you will have a curve like this. That means, if I have a higher conversion, in that case my production cost per ton of B just from the reactor comes down. And similarly, if we plot against Y the recovery of cost, that means the recovery cost is basically in rupees per metric ton of B in 1 metric ton feed to column. That means, basically it is related to the feed and the feed concentration. Then you will find that initially if you produce, it will keep on going up. That means, if you recover more and more, there will be a sharp increase in cost. So, what your final cost total is basically a function of X and Y. Ideally, you would like to operate here as low as possible practically. Ideally, you would like to recover as high as possible actually. But since if you look at this and if you solve such a problem, you will find there is a combination of X bar and Y bar, which are the corresponding values of X and Y, which optimize the total cost. And that is the optimized design for such a system. This is what I wanted to say in my last class, and this is something which is very important, particularly while you are designing large systems. We also have talked about bringing in new conditions, particularly when your number of design variables are large. That means, your objective function, like the cost here, is a function of a large number of variables and a large number of constraints, particularly if they are non-linear. You will always find there is a possibility of having multiple solutions to your optimization problem. That means, there is a case of tie between the solutions which have the same objective function. And in order to break the tie, you will be required to bring in new considerations, and these considerations could be what I am listing here. The first thing, it could be the multiple optima. Definitely we recognize, for example, in large process plants like refinery or fertilizer, they do exist. An example of this is more than one combination of the plant capacities for generating maximized profit of your plant. That means there are alternative operating or alternative design options for the refinery or the fertilizer complex. So we have to break this. That means out of these options, we normally bring in a new criteria. A typical such a criteria could be the ease of maintenance, as I have listed here. You could also bring in a criteria like lower amount of pollution among these two competing options, and decide based on which criteria you are going to set your actual plant, which has the same optimum objective function. That means the economic objective is the same, but you are bringing in of the new criteria, which could be either a quantitative criteria or a qualitative criteria, as the example of maintenance and pollution that I have given here. You definitely can design this. In case of specific equipment optimizing, the design usually will involve, instead of economic parameters, suitable technical criteria like the furnace efficiency, which could be an optimum alternative. That means, instead of economic optimum, what you do is you try to maximize the efficiency of a problem. So, basically I reiterate again that when you design a complex or a large system, you definitely need not always maximize the individual units. It is the whole optimum combination of the different units and the sub modules, which need not be maximized or minimized or optimized individually, is to be seen at. When we are talking about the designs and the design consideration, we should also remember a few things. There will be, see, our design is basically based on certain inputs, but these inputs are decided by us. It is not sure that exactly the exact value of the input design that has been used will be available when the design comes to practice. Robust design is one in which the design which I am producing can tolerate input variations, the design input variations within a limited level. We normally resort to safety factors. That means, we slightly over design when we have to take care of certain uncertainties, but there are mathematical techniques to evaluate such uncertainties and the robustness of a design mathematically as well, which we are not going to deal here in details, but there are techniques for this. We will know this much. Normally it is based on a sort of statistical random simulation of your design and looking at the result of that. When we are talking about additional design considerations, one of the major things is the compatibility with the rest of the plant. That means, if part of the plant has been designed as per the ASME code, it is desirable that whatever new design that I make should also conform to that in order to make it compatible. The reliability of the process and mechanical designing of equipment definitely is greatly improved if we refer to the relevant standards and codes. There are codes which relate to the material quality, there are codes which relate to the design of pressure vessels, there are codes which relate to the design of heat exchangers and columns and other things. And definitely making a design as per the code gives us certain advantages like interchangeability of equipment, reliability of equipment, and following a uniform code will definitely attract less amount of insurance price, which is normally, particularly for hazardous plants, a large fraction of the operating cost, a reasonably large. There are practical considerations which have to be there, like the available space for the equipment, the ease of operation and maintenance, and certainly the safety during the erection, commissioning, maintenance and operation. It cannot be ignored. We talked about a reliable design. That means the first thing, the design has to be functional in practice. That's the first and the foremost requirement. The second thing is the design has to be reliable. That means if I am designing for a client, the client should be confident that I have designed it correctly, and he gets much more confidence in me when I tell that I have designed this as per the standards or certain design codes which are applicable for his specific design case. We definitely will be generating some sort of compatibility with other equipment which are designed with the same code. It will make the design reliable, it will ensure interchangeability, and there are material standards which ensures that the material which is available and which is being used or to be used for my design is of standard quality. Basically, the use of standards help in another way by reducing the delivery time and generating a reliable design and to get it fabricated. Perhaps now we should focus on the process design problem. Normally, whenever we design a process, we need to know the boundary limit. That means whatever streams are input to this particular boundary and what are the output streams leaving this boundary. We definitely have to have an idea about the required capacity. It is 6 tons per hour or 0.6 ton per hour. The spatial location and its limitation, for example, the space available, the contour of the ground on which we are going to build this, if we need the wind direction in order to have a proper safe orientation of equipment. We definitely need to decide on the specific standards to be followed for designing. So, these are the basic minimum requirement before you start your design. Now, the problem of design is rather initially pretty vague. Your client will have an expression that he would like to have a plant which manufactures ammonia. So, what he does is he expresses his functional interest. Then, listening to that, the designer will conceptualize the product design. That means the product is basically the design which he has to deliver, and what he does in his mind, he definitely will be considering different technologies for this ammonia plant. But all these will initially be done mostly in his mind without doing any quantitative calculation. That means, he heuristically thinks and he heuristically decides these are the companies and these are the technologies perhaps which can meet the requirement of my client. Based on the heuristics and experience, he decides finally a finite number of alternatives. Now, based on these, at this particular point, a preliminary design specification which is much more detailed than the functional interest, which is typically called the PDS document, is produced. It attempts to identify and quantify the design deliverables. That means, this outlines clearly the deliverables from the design, the capacity, the material, the process, fluid properties and such things. This marks the start of process design. If we look at the deliverables, when we are talking about a complete design of a process plant, that is the deliverable. Now, the question is, what exactly is a complete design? It simply can be in brief said that it should be your delivery of the design document should be such a document which will contain the complete design of a process plant. That means, based on this, possibly only the detailed engineering can be done, and then the fabrication of the equipment can be done, erection can be done, the plant can then be started. I have used a term basic engineering. The basic engineering document is normally supplied by the technology vendor in the form of a basic engineering package. A typical example of this is a Xerox plant, which is meant for removing mercaptans from light hydrocarbons, is a technology which is sold by Universal Oil Products Methods EOP. What they do is, to the client they provide a basic engineering package. It talks about the process, the equipment selection and the selected vendors from which the equipment can be purchased. It includes a PFD, it includes a P&ID. I will detail these two after this, immediately after this. It has a functional description of the system. It has an overall suggested plot plan. The process design is after this and is expected to be optimized. This definitely is a document on which the detailed engineering is started. The detailed engineering will definitely involve codes and standards. The deliverables, the first thing whenever we are talking about a process design will be a flow diagram, and it is going to be a block flow diagram. That means the sub processes being conceived as blocks as shown in the figure here presented. These are the individual blocks. If you look at it, it provides the overall idea of the large and complex plants, what all sub blocks or sub plants it consists of, but it contains and displays only the important features. Next is perhaps the starting basis of the detailed design. Now, for this what you require is a process flow diagram, which must contain and show all streams, major equipment, interconnection with other systems, the bypass and the circulation lines, system ratings, particularly the pressure, temperature, if there is any such thing which has to be specifically mentioned, the operating values and the composition of steam. Now, you definitely will be having a stream table, which basically is the table that you can see here below the diagram, which contains stream number wise the stream details, which includes phases, temperature, pressure, enthalpy and flow rate. This is the same thing separately shown. After all, you have conceived a plant, you have decided on the alternative designs, you have come to a state where the process is finalized, the process streams are identified, all the equipment are identified, the details of the plants and instrumentations are also known. Now, how to document these? This is done in a document which is called the piping and instrumentation diagram, or P&ID. The P&ID definitely shows the functional relationship of the piping, instruments and the equipment. All piping, including safety and any emergency handling facility, is also shown. The control and instrumentation components are definitely shown here, and this gives us an idea of what exactly is the parameters controlled, what are the parameters measured, what are the relationship between the different individual equipment, how this material flows from one equipment to the other through the pipes. Naturally, if you are to build a plant, you require a plot. So, the plot plan shows the plant layout which definitely will be including and very clearly showing the relative location of the equipment in a scaled plan. For example, if you have a particular wind direction, a furnace usually is located downwind so that any heat from the furnace does not affect your plant, or it is conducted away without affecting your plant in a safe location. In order to show the equipment and the individual piping, you must have the details of their spatial location. That means the isometric drawings are usually essential in order to have a 3D view or a 3D idea of your plant. So, you have the isometric drawings of the equipment and the piping and the structurals as well. For example, if you have a pipe rack, naturally you require an isometric drawing of the same as well. Now, once you have completed these things, at least in a preliminary fashion, you have to ask for fabrication of your equipment. So far what you have completed are going to be the input of the fabrication. So, the fabricator has to be given the fabrication drawings, which he reviews first. Maybe he will ask for a set of clarifications from you, the designer, and when these are finalized, the fabricator starts fabricating it and finally delivers it to the site. I think I will stop here today, and with this the design overview is fairly complete for your work or session. Thank you.